Sometimes theorems are more complicated, and so even using coordinate geometry, their proofs are a little bit longer, but still much easier than trying to do it using traditional methods. For example, do you remember the trapezoid mid-segment theorem? We did not prove that when we first introduced it to you, because using conventional methods, it would require it would just require a massive amount of work. So we're going to prove it at this time using coordinate geometry. Warning, it's not going to be short, but it won't be difficult. In the trapezoid mid-segment theorem, we are told that we have a trapezoid and that we have a mid-segment, which is the segment that connects the midpoint of the two legs. So let's place a trapezoid on our coordinate plane. Notice how I've placed one of the bases across the x-axis and one of the vertices at the origin. And then we'll throw in the names of the other vertices. So here we have trapezoid trap. And because we're dealing with mid-segments, we're going to be dividing things by 2. So let's use variables that are easily divisible by 2. For r, I'm choosing 2r and 2q. Now because RA has to be parallel to segment TP, and TP is along the x-axis so it's horizontal, I'm going to choose a y-coordinate for A that makes it horizontal, namely 2q. The y-coordinates have to be the same to make a horizontal line. And then for my x-coordinate, 2A. It's not related to any of the other points, so we can use a different variable. And then of course for my P down here, we will use 2P, 0. And now we have our midsegment MS. And what are we trying to prove? Well, the trapezoid midsegment theorem says two things. First, that segment MS is parallel to the two bases, and that the length of segment MS is the average of the length of the two bases. Or some people will say half the sum of the lengths of the two bases. Alright, so now we know what we're given and what we're trying to prove. Let's get started. And we'll start by, of course, finding the coordinates of our midpoints, M and S. So adding the x coordinates together and the y coordinates together, dividing each of those by 2, we find out that the coordinates of M are R, Q. And now we'll find the coordinates of S. So we'll add the x coordinates together, the y coordinates together, divide both of those by 2, and we find out that the coordinates of S are A plus P, Q. Don't worry about the fact that our x coordinate has an addition problem in it. That's no big deal. But now that we have all of our coordinates, I'm going to clear our screen, and we're going to start by proving the first part, that segment MS is parallel to the two bases. By definition of trapezoid, we know that the two bases are already parallel. That will make our life a lot easier. Now we can use the slope formula to show that the mid-segment is parallel to one of those bases. Well, what is the slope of the mid-segment? Well, that's the difference of the y-coordinates divided by the difference of the x-coordinates. Well, q minus q is 0. And 0 divided by anything other than 0 is 0. So that's an easy slope to find. Now let's find the slope of segment TP. And, well, both the y-coordinates are 0, and 0 divided by anything other than 0 is 0. Since the slopes are the same, we now know that segment MS is parallel to segment TP. But we have the transitive property of parallelism that then tells us that all three of our segments are parallel to each other. So we have just proven the first part of this theorem. Notice I said it wasn't going to be short, but it's not going to be difficult. We just used the slope formula twice, proved that lines were parallel. That's easy, right? Not necessarily short, but easy. Now let's talk about the lengths part. That's going to be a little bit longer. And to do that, we will need to use, of course, the distance formula to find the length of all three segments. So let's start with our mid-segment. Notice that we're going to take our x-coordinates, subtract them, square them, and our y-coordinates and do the same. The nice thing here is because our y-coordinates are the same, they're 0. So they just move out of the equation, and we can take the square root of something that's squared. So we end up with A plus P minus R. And I'm just going to do this quick little thing here where I'm going to rearrange things using the commutative property of addition, and that is the same thing as A minus R plus P. And you'll see why I did that later. Now let's find the length of segment TP. Once again, the y-coordinates are 0, so they reduce out. And the square root of 2p squared is simply 2p. And finally, the distance between the points R and A. Notice once again that the y-coordinates are the same. 2q minus 2q is going to be 0. So we take the square root of the quantity 2a minus 2r squared. And the square and the square root in this case do reduce out, leaving us a minus r. So now we are going to have to use some algebra with all of this. So keep all of these lengths in mind. Let me clear the screen. So now our algebra. Remember that we just found the lengths of all of our segments. The length of MS was a minus r plus p, the length of segment TP was 2p, and the length of segment RA was 2a minus 2r. Now, to get us started, I'm going to use the addition property of equality and add 2p to both sides of the equation for RA. And of course, since TP is the same thing as 2p, we end up with this equation. Now this is all fine and dandy, but if you notice in what we're trying to prove, we have this 1/2 here. So I'm going to introduce 1/2 to this equation by simply multiplying both sides by 1/2. Remember, you can do the same thing to both sides of the equation, and it's perfectly legal. So now on the right-hand side of the equation, I'm going to distribute that 1/2. And of course, 1/2 times 2a is a, 1/2 times 2r is r, and 1/2 times 2p is p. Oh, wait a minute. Do you notice something? Look right back up at the top where we said that the length of segment MS was a minus r plus p. And down here at the bottom on the right-hand side, we have a minus r plus p. So that tells us that we can use the substitution property to say that the length of MS is equal to 1/2 the sum of the lengths of the two bases. Wow, isn't that just what we were trying to prove? Once again, this is not short, but using the distance formula and the rules of algebra, it is not difficult. Don't be afraid to do a lot of work.